Good morning, this is Sherry Kraber. Welcome to our ISEA webinar. I would like to introduce our moderator for today, Dr. Lynne Hare.
Thank you, Sherry. Good morning, everybody, and welcome to this webinar on the new, brand spanking new handbook for ISEA. We're happy to share this information with you. I am speaking now because I am the so-called editor-in-chief, and I obtained that distinction because I was the last person in the committee room to put finger on nose. So by default then, I am introducing this handbook to us this morning. I hope you will learn from what you see and take pleasure in all of it. What I would like to do is introduce just broadly the information on the outline that you see before you here, why it was written, what's in it for you, who wrote it, and where it is going. And following a brief introduction, we will have the chapter editors each give a description of what's in those chapters. There'll be a brief discussion after that, and we will open to questions and answers as appropriate. So first off, why was this written? And I'm here to tell you that this handbook is not your grandparents, not your parents, not even your statistic book. This is very different. It's not a book about all of statistics. This is a book about the doing of statistics. And as such, it talks about leadership tools, organizational tools, or organizational functions. And a good deal of it is on the how of doing statistics in large organizations, whether they be corporations or other big organizations involving many people and complex problems. We focus on dealing with solving large unstructured problems. This requires a very broad perspective on organizational problem solving, and we present a good deal of information on that. It requires more leadership than a lot of statisticians are used to exercising, and we talk about methods to engage in that kind of leadership. We do not present theorems and proofs. We do not present toy problems. We talk about the doing of statistics, and we believe that there's little else in the market that does this. So what's in it? We start out with a broad introduction, definitions, fundamentals, framework, principles, and a history of statistical engineering, some of the core processes. We talk also about our enabling technologies. We introduce a holistic approach involving some tools for teams, some disciplines necessary, many of the soft skills going into organizational leadership, and so on. That's the second chapter. The third chapter is on data collection, involving the things that challenge us in data collection. I'll describe that in a while. The issues of data pedigree, measurement systems analysis, design of experiments. We go into some detail on design of experiments because it's a very important tool in statistical engineering. We talk about data exploration, cleaning up data, how to display data, how to examine what's going on in the data before we engage in any data modeling. Then we talk about drawing inferences on the basis of data, variation and bias, statistical intervals, so on and so forth. That will be described in some detail later on. And then we talk about the solution and identification deployment, iteration for solutions, organizational environment, finances, and hurdles encountered in doing all of this. And then finally, at the end of the handbook, we have some case studies that provide examples and further edification. Now, why should you be interested in this? What's in it for you? This is a handbook, and there are lots of gems in this handbook, and the handbook is written, as you will soon discover, by people who have been to the city and seen the elephant. They are vastly experienced. They've done these things, and they've used these techniques, and they have demonstrated effectiveness with them. That we provide a wide diversity of material at a high level. We don't go into a lot of technical details, as I said earlier. There are no proofs, there are no derivations, there's no computer code in here. We don't support one computer code over another. We're not going to get into arguments about which is better, R or Python. And we don't recommend whether you should use JMP or Minitab or Statistica or some other package. That's up to you. That's not our purpose in here. So that's what's in it. And what's in it for you, if you go through the handbook and use it as a resource, or if you use it as reading material for edification, you will get tangible results when you start to practice all of the points that we talk about in here. You and your organization will experience some growth. You might even get some advancement because of increased influence that you exert in the organization. Fame and fortune coming your way. You'll have a greater feeling of self-worth, more esteem, more fortune, and net, you will be much more successful, and you'll have the gratification that comes with that. Now, this handbook has many authors. There is a list right here of contributors. All of these people are just vastly experienced in this effort. The last name there might be new to you. That's Lisa. Lisa served as an assistant editor, and she went through and helped clean up the text, and she did yeoman's work in that effort. I wanted to mention also that we this last year in April we lost one of our contributors, Dean Neubauer, and we are sorry that he has passed. He's no longer with us, but he contributed nicely as well. We have 5 chapter editors, Ronald Does, Lynne Hare, Roger Hoerl, Susan Schall, and Ron Snee. And these people will soon describe the various chapters that they have edited, where we're going with all of this. This is a start, and it is only a start. We want to add additional case studies for greater edification and examples for people. There will probably be more chapters on other helpful information. When new technologies emerge, we hope to grasp those and include them in the handbook. We will have more authors. We will keep this handbook evergreen. So with that in mind, what I'd like to do is give each of the chapter editors an opportunity to describe the contents of the chapter that they were responsible for. We'll start with Roger Hoerl. Roger, many of you already know Roger or know of Roger. Roger is assistant professor at Union College. He's a previous chair of ISEA, receiving his PhD from the University of Delaware's PhD in statistics. He's a fellow of the ASA and a fellow of the ASQ. ASA recognized him with its Founders Award and the Deming Lecture Award. Roger has received the Brumbaugh Award and the Schuhart Medal from ASQ. Roger edited much of chapter 1 and also co-edited chapter 5. He will speak on both of those. So Roger, if you would please, I will switch slides for you if you like. You tell me when to move, and we'll get into your section.
Please. Well, good morning, good afternoon, good evening, depending on where you are as you're watching this webinar. Thanks very much for coming. And what I want to do is sort of explain to you what is in the first chapter of the ISEA Handbook on Statistical Engineering. It's an introductory chapter. Susan is going to talk shortly about chapter 2. And I would say these are really the most unique relative to a statistics or data science textbook. I'm frequently asked, well, what's the difference between statistical engineering and X? And X could be analytics, data science, machine learning, so on and so forth. And if you're wondering, well, how is statistical engineering really different? If you read chapters 1 and 2, I think it'll be quite clear, because I don't think you're going to see this material in traditional statistics textbooks. If you do, let me know, because I'd be interested. So this chapter really answers that question of what's unique here. It explains what statistical engineering is, including a specific definition from ISEA, its history, where it came from. We also use the analogy to understand statistical engineering, that statistical engineering is to statistics as chemical engineering is to chemistry. So we explain that in a little more detail and then talk about some of the fundamental principles. Now, 3 of the key aspects of this are the typical phases of statistical engineering efforts, the key principles underlying the utilization of statistical engineering, and what we call the core processes, which are basically the what's as opposed to the how's. And I'm going to go through those on the subsequent pages, but net, I would say chapter 1 really explains the key concepts underlying statistical engineering. Next, please. So these are the phases of typical statistical engineering applications. Importantly, there's not 6 easy steps to solving large, complex, unstructured problems. These problems are messy. There's a lot of feedback loops, but these are typical phases and provide a framework for how to think about attacking these problems. First of all, of course, we have to find the right problem. And as we know, in many cases, the problem stated originally is not actually the right problem. We have to dig a little bit to find out the right problem. And then in many cases, what we see is kind of a mess. There's a lot of things going on, a lot of moving parts. Everybody has a different opinion. And we have to sort of peel back the onion and figure out what's the real problem here? How can I accurately define and structure the problem we need to solve? Once we do that, for simple problems, we just pick the best method. We can pull that out of a textbook and we're off and running. For complex problems, they've been there a while. They're there for a reason. There's a reason nobody's solved it yet. And for us to make any progress, we have to dig and really understand the context of the problem, where it came from, what's been tried before, what are the politics involved? Are there people that actually don't want this problem solved? Once we have a really good understanding of the context of the problem and it's well defined and structured, for large problems, we generally need to develop an overall strategy for how to attack them. That typically involves multiple tools, not picking the correct tool, but rather figuring out a sequence of tools. Strategy, unfortunately, is not a word we hear about a lot in statistics, but is very important in statistical engineering. And then, of course, we actually have to do something. We develop and execute tactics. This is really the first part where we're likely to do a lot of data analytics. Once we do the analysis, implement the tactics, we still have to figure out what's the right solution, deploy it, and make sure it's sustainable over time, which Ronald is going to talk about more a little later. Next slide. When we think about what's required to address these large, complex, unstructured problems, there's 5 fundamental principles that we have identified. Basically, what we're saying is all problems don't require all 5 of these, especially fairly straightforward problems, but complex problems, problems that are very difficult, that have been there for a while, that are maybe unstructured, generally require us to do all of these. One is to understand the problem context. I mentioned that already. Now, don't assume that what's stated is all there is to know about the problem. We typically need to develop an overall strategy, not just pick one tool. We talk a lot about understanding the pedigree of the data, or where the data came from. It's very easy in statistics textbooks to just say the data are a random sample from the population of interest. Very easy to write that in a textbook, but of course, if we're working on real problems, it's virtually never achieved. So all data has some limitations, some more than others, and before we decide what we can and can't do with this data, we have to really understand where this data came from and what its pluses and minuses are. The integration of sound subject matter theory is almost always critical for these big problems. They're not just data problems, but they involve a lot of subject matter knowledge in marketing, in healthcare, in physics, whatever it might be. And then, as I said, since we need a strategy, that means we're going to need a sequential approach. It's not a matter of picking the one correct tool. If you look at the case studies that are posted on the ISEA website, you'll notice they generally follow the overall process I just showed, and then you'll see each of these key principles played out, particularly sequential approaches. Next. When we talk about the core processes, what do we mean by that? Well, there's a lot of tools out there, especially if we throw in OR, data science, related disciplines. Maybe there's thousands, I don't know. And it can be very confusing, but if you kind of boil it down, there's a few major things that we do in the analytics space, and we call these the core processes. So our strategy usually involves some combination of the core processes. Data collection, you're going to hear more on that. Data exploration, you're going to hear more on that. Model building, we're not going to get into that today. That's dealt with very well in a lot of the other textbooks that are out there. Drawing inferences or learning, those terms are used quite a bit, but I think a lot of times they're misused. So we're going to talk about that a little later today. And then solution identification and deployment, as I said, Ronald's going to tell us more about that. So that's basically what we have in chapter 1. And now I'm going to turn it over to Susan Schall, who's going to talk about chapter 2.
Thank you, Roger. Most large, complex problems, as Roger said, are messy. And they are messy because they involve the most unpredictable element, people. As an undergraduate industrial engineer, one of my professors said that there are 2 solutions to a problem. The correct solution, which all the theory and textbooks and analysis tell you to implement, and the right solution, which is the one that you can implement with and through people. So people are key to addressing these large, complex problems. What this means to the statistical engineer is that we need enabling technologies of leadership, communication, collaboration, or teamwork. Next slide, please, Lynn. We address these 3 enabling technologies in chapter 2. The first that we address is leadership, where we define leadership as the capacity to translate vision into reality. And that the work of leaders is threefold. You can go ahead there. First, to craft a vision, that is to explore possibilities, being bold in doing that, but testing assumptions. Secondly, build alignment, that is getting everyone moving together in the same direction with clarity and dialogue and inspiration along the way of doing that. And then thirdly, championing execution, providing momentum, structure, and feedback in execution. Next slide. The second enabling technology that we address is communication. And communication is the ability to share information that mobilizes people around what is most important. The statistical engineer must communicate crisply consistently and in a timely fashion, knowing their audience, explaining the rationale behind decisions or analyses that were made, addressing people's concerns and meeting them where they are by incorporating stories and graphics into their communication. You can hit again, Lynn. Stories, as the oldest form of communication, stories will be remembered long after people have forgotten the facts. So they are an important element in communication, as is graphics. You could do again, Lynn, because they help to turn data into information that people can use and understand. You can, next slide, please. The third enabling technology that we address in chapter 2 is teamwork, and we define a team the same as Katzenbach and Smith do in their seminal work, The Wisdom of Teams, as a small number of people who are committed to a common purpose, performance goals, and approach for which they hold themselves accountable. We address the effective elements for a team of you can hit again, Lynn. This builds again. So we address the elements of effective teams of shared purpose, commitment, leveraging the knowledge, skills, and abilities of the team members, communication, piggybacking off of the previous subject, managing meetings, making decisions, handling conflict, and most importantly, planning for and obtaining results. Next element. A statistical engineering team, like any team, will go through the 5 phases of forming, storming, norming, performing, and adjourning. Next, the difference here is that a statistical engineer will bring some other tools to help the team move smoothly through these 5 phases, and those may include brainstorming, affinity mapping, interrelationship diagrams, multi-voting, cause and effect diagrams, flowcharts, 5 whys, and perhaps a host of many other tools to help the team move through these phases. So those are the 3 enabling technologies that we address in chapter 2. And I just want to take a moment before I turn it back to Lynn to mention that chapter 2 was really a collaborative effort. We demonstrated the teamwork element here between myself, Roger, Ron, and Lynn. Back to you, Lynn.
Thank you, Susan. I am remiss. I did not get a chance to introduce Susan to our audience. Let me back up. It is really Susan O. Schall, and she takes advantage of that middle initial to make her organization SOS Consulting. And she is indeed a savior. She has helped many organizations solve problems, saving over $250 million and transforming manufacturers to compete more successfully in the future. Prior to her entering into her consulting career, Susan held technical leadership roles at Kodak, DuPont, GE Lighting, and R.R. Donnelley. She has a bachelor's in math and then BSMS and PhD degrees in industrial engineering from Penn State. She's an ASQ certified quality engineer, certified master black belt, and so on. She's been recognized for professional achievements and contributions to industrial engineering by the Institute of Industrial Engineering, IISE, and she's named as a fellow in 2020 and received their Medallion Award in 2018. And she's a Marquis Who's Who top executive and woman of influence. She has greatly influenced our thinking and assembling this handbook, and we owe her a debt of gratitude. Next up is Lynne Hare, and I have the dubious distinction of introducing Lynn. My apologies to those of you who thought Lynn might be female. My parents were sorely disappointed, obviously. I've been consulting for the last 12 years. Prior to that, I had worked at various companies, Unilever, National Institute of Standards and Technology, and Nabisco Craft, and a fellow of ASA and ASQ. Have been working around from various organizations. I just can't keep a job. And I have an undergraduate math degree from Colorado College, and then MS and PhD from Rutgers. As I mentioned, I took on this position of editor-in-chief, and am extremely thankful for all of the people who contributed to it. We put together what I think you will agree once upon your reading that it's a very successful enterprise. Chapter 3 is where I edited with the help of several other people named earlier, and there's some the focus of chapter 3 is on data collection. You know, how do you get data? How do you know what's the right amount of the right kind of data? One of the key elements of that was the data quality, and how are we assured that what we get is essentially clean data. That is, that it's not been tampered with. We know its history. We know who it's been hanging around with. We know of opportunities to get in there and mess things up, and we're assured. And there are sections in this chapter on data pedigree, and Roger also mentioned that in the first chapter. We talk a bit about the importance of precision and accuracy. If we don't have the proper measurement systems, then we're just busy with numbers. And so we spend some time talking about how people might go about obtaining accurate and precise measures, and describe devices for doing that, such as gauge, R&R, and other tools and technologies. We talk about getting the right amount of the right kind of data, rational subgroup sampling, representative sampling, to assure that what we have is as close to unbiased data as possible, and as close to being representative of what's actually going on in the process as possible. We spend a good deal of time on the statistical design of experiments, and we go into some of the history, and the reason for that is that unlike what we've seen in teaching of chemistry and physics that have been around for ages, experimental design technology has been around for about 100 years, plus or minus, and it continues to improve as the technology improves. And so it wasn't until about the 50s or 60s or 70s that mixture designs came to the forefront. But one thing that's not taught in textbooks as much as I certainly would wish it were is the usefulness of designed experiments. People tend to think of it as some kind of a tool for assessing many variables at the same time, assessing the effects of many variables at the same time. And while it does do that, its main thrust is to build knowledge. And so it's not on the basis of the results of design of experiments and the concomitant hypothesis tests that it affords, so much as it is the fact that we are building knowledge as we go through the design of experiments process, from screening designs to characterizing designs to optimizing designs. And it is that increased knowledge that helps us find the sweet spot. And that is too often ignored. We talk about finally obtaining data for effective and sustainable solutions, and we even dabble into some things about what we must do to create sustainable solutions. That's the subject of a later chapter. Our next speaker is Ronald D. Snee, and Ronald assures us that the D does not stand for DO. Instead, Ron is a very bright and very capable individual We've known each other for years. Ron is the founder of Snee Associates, LLC, dedicated to the successful implementation of process and organizational improvement initiatives using quality design, continued process verification, Lean Six Sigma, and other data-based improvement approaches. Ron is just an incredible leader in the entire statistical community. He has awards out the years. He's an honorary member and fellow of the American Society for Quality. He's fellow of ASA, fellow of the American Association for Advancement of Science, and academician in the International Academy of Quality. He's received the Schall Award. I think we have 3 Schall Award winners on board here, Ron and Roger and Ronald Does. And Ron, to go on, Ron is ASA's Deming Lecturer, Dixon Consulting Excellence, and won the Jerry Hahn Award. 330 papers, 8 books. We're waiting for him to do something productive, if you get my meaning. So Ron, if you would please take it away, and I will be honored to flip your slides.
Introduction, and I'm still working on getting it right, so to speak. So we're talking here about data exploration, and if I can get that phone out of the way. In chapter 4, and as a basis, statistical engineering really is a data-based methodology. Lynn, this is a build slide, so you're going to have to keep clicking away.
Okay.
There you go. So it's a data-based methodology, and of course, at that database, data exploration is a key step. As a matter of fact, it's basically the first step in data analysis. And it's really helping the analyst understand the data by assessing the data pedigree and to characterize the variation of data so we can help develop causal relationships and so forth. Next. There's 3 important aspects of data exploration that's discussed in the handbook, and they're there as you see them. The philosophy of data analysis, exploratory data analysis. You need to keep in mind where it comes from. We'll talk about data cleaning, which Lynn mentioned a few moments ago, and then finally we'll talk about making use of exploratory data analysis rather than an academic subject. Well, we're going to talk about how to use it. So next point. The exploratory data analysis was pioneered by John Tukey, famous Princeton professor and statistician at Bell Laboratories, really going back into the early 1960s when he started to promote the idea. It had been used a lot by others, but the term was really Tukey. And so next step, it's the widely recognized as the initial step in data analysis, the whole idea of exploratory data analysis. Defined, a definition is the philosophy of critical thinking about data and the data pedigree, along with the concepts, methods, and tools of data analysis. It really calls for being alert at all times for unexpected patterns and relationships and extraordinary cases. And what happens by doing that, you develop the variability, understanding of the variability, and so forth. Key to that, which has been mentioned, and hopefully you'll see that in the presentations as we go along, is graphical visualization of data, which is really central to exploratory data analysis. Tukey has a great quote, which I think says it probably best of all, is he says the greatest value of a picture, i.e. a graphic, is when it forces us to notice what we never expected to see. So generally, you have a set of data and you're trying to understand it, identify the important variables and so forth. And it's only after you have constructed a graph all of a sudden you see things that like Tukey says, you never expected to see. So one of the things that Chapter 4 in the data exploration part provides is something called the global positioning system. And basically, exploratory data analysis, it's a journey. And so we provide the GPS, global positioning system, for exploratory data analysis to help guide you along this journey. Now, I'll return to this whenever I have some concluding comments, but I'm going to skip by that now and move on to the next subject, which is data cleaning. Next slide, please. So what is data cleaning? Lynn mentioned that a little bit. It's about detecting and correcting errors in the data that are being analyzed. In this section, we talk about 5 types of dirty data. If we're going to clean it up, it must be dirty in the first place. And things like logical errors, inconsistent but outlying atypical values, data duplication, missing values, and outliers or atypical values. And so we talk about how to clean that data and get that out of the way. And in a way, the best practices is we talk about that, about how to reduce or eliminate errors at the source. So you want to get at where these errors came in the first place, creating a standardized procedure or checks for data being analyzed. Consider the various unique features of a particular data set. When you understand those features, then that gives you an idea about the data pedigree and how to check to see if you've got any problems. And of course, the last point there is importance about formulation of communication with the owners of the data. Almost always, I shouldn't say always, but typically you got people who are analyzing the data. You have people that own the data, and whenever you're trying to clean it, you need to go and check with the owner on various aspects to get make sure that you get all of the quotes dirt out of the data. The last section that in Chapter 4 is about using exploratory data analysis, talking about how to use it. And as I mentioned earlier, we're going to use it to understand the data prior to the statistical analysis. And it helps through the graphics to help the analyst identify unexpected patterns and relationships and extraordinary cases. Some of the tools that we mentioned here are, by no surprise, graphical tools. We also mentioned descriptive statistics as well. It can be helpful. On the graphical side, we talk about the Magnificent 7 graphical tools. You see them listed there. No surprises there that what the tools are, and but these are the tools that get being used over and over and over again. So while there's more sophisticated tools, these tools are really particularly useful. 2 tools that I like to emphasize, and it is in this section, is scatter plots, of course, to identify relationships, but more importantly is the time sequence plot, which is really useful in studying the variability over time. Here's 2 examples. One is in the Dow Jones Industrial Price over 1990 to 2019. And you see it bouncing along there, and you see the dips. And if you look at the very end of it, which is more recent, you see a lot more variability that we're used to seeing. And of course, that's characteristic as you would expect the market. On the other hand, on this other one on the right-hand side is a plot of process yield versus batch for a blockbuster pharmaceutical product, which was having a lot of concerns about the yield in the product. And when this time plot was constructed, lo and behold, there you can see there that there were different batches were producing the variation it was seeing and creating the yield problems. Well, it turns out that whenever the different batches of raw material, I should say, the different groups of data that you see there, that led to, when that was discovered, they were able to figure out how to clean that up and save, really, in this case, millions of dollars. The key thing about the time chart is that it identifies sources of variation, which you wouldn't think any other way. And in that, of course, by identifying when these variations occur, you get an idea to where to go to put on your hat as a detective. I'll get it here in a minute, and to identify what the various variables might be. Lynn mentioned that he and I are graduate students together. We've known each other for a long time, and our major professor at Rutgers University, Ellis Ott, used to point out the importance of the time plot, which doesn't seem to be recognized in our experience as well as we think it needs to be in the data analysis, data science community. So I recommend that for your consideration. So with that, having said all of that, we're going to conclude here with some best practices. One is you need to adopt an inquisitive and skeptical mindset. You want to be a detective, forensic scientist, what have you, about the data. The second point is that you need to, if we can get Lynn to get it up here. There you go, data exploration. It's a journey, and you need to plan accordingly. Recognize that you're going to learn things about the data and about the process. You can learn about when you need more data and so forth. Next is that you're going to be making extensive use of graphics along the way, and expect these displays, as we mentioned earlier, to reveal the unexpected. The next point is one of the first graphics to use, as I mentioned just a moment ago, the whole idea of a time or sequence plot. Almost all data are collected in some type of a time or sequence, and by plotting it versus time, you're going to identify important points. Next one is be on the lookout for non-random patterns, things that just don't look right. That can help you maybe clean up the data, suggest variables that we can use to model the process and identify important variables. Next. Focus on parsimonious models, the critical few of variables. It's been our experience and a lot of others that typical for a process, there's 3 to 6 key variables that are driving the process. These are the process. Whenever you look at the graphical displays and you do the exploration, you're going to see variables which have big effects. And we typically see 3 to 6 as being critical. Next point is exploratory data analysis is inherently subjective. You're looking at graphics, you're bringing in subject matter knowledge, the data pedigree. The whole idea is, and you're bringing in your experience, and that's basically subjective. And you're not into the modeling and exercising all of your quantitative skills at this point. You're trying to learn how to solve these large, complex, unstructured problems by looking at the data. And so with those comments on exploratory data analysis, I will turn it over to, I think it's Roger's next, isn't it?
Yeah, Roger is up next, and he's going to talk about drawing inferences. I wanted to interrupt just a second and mention that Roger is largely responsible for overseeing the development of this handbook and coaching and cajoling, and we think that he's done an excellent job. Roger's going to talk to us now about the chapter on drawing inferences. Go ahead, Roger.
Thank you. So you might think statistical inference, it's been around for a long time. It's in every textbook. Everybody understands it. What's the point of even discussing it? Well, I would argue that statistical inference is one of the most misunderstood topics among our students. And that's true at every level, from intro to advanced. And I'll give you an example in a minute. So what's unique about the handbook versus the treatment of statistical inference, say, in a statistics textbook, is we really focus on the why and the what, as in, why are we doing this in the first place? What's the point? Most students don't understand that. And then, what are we actually doing when we do statistical inference? Now, in my experience, most textbooks talk about how to do it. So they give you formulas, they give you code, they give you examples that we have this data, we calculated this confidence interval, and students can figure that out. They can push buttons on the computer, but they're still left wondering, well, what did we just do? And particularly, why did we do it? So while the methods are included, the real focus is on the why and the what. We also explain as part of the what statistical inference actually is. Now, those of you out there may be saying, well, that's obvious, everybody knows that. I don't think that's true. And I think it's especially true for people that are not professional statisticians, say applied mathematicians, engineers, computer scientists. Statisticians often have had it beat into them and eventually kind of get it. But here's a real example that I've seen more than once. I've seen this particular example and then similar ones many times. Somebody will take a population of data, like the entire student body at Union College, and they'll do some statistical analysis. And then they'll say, we did a comparison of male versus female GPA, whatever, and the result is statistically significant. And I'm sitting there thinking, well, wait a minute, you just analyzed the population. So what do you mean statistically significant? The concept of statistical significance means we're applying this not to the data in front of us, to a broader population. What's the broader population that you think this data is a random sample from? And then I kind of get the deer in the headlights look, like, well, wait a minute, this is the formula, it's in so-and-so's textbook to calculate the F ratio, T ratio. And I say, no, I'm talking about inference. You have a population. If you're going to do inference, you have to treat this as a sample from some other population. What is that population? And then I want to find out, is this really random from that population? And over and over again, I just get a deer in the headlights look that people have no idea what I'm talking about. They're following the formula that was in the textbook, not realizing it's based on a higher level concept. So we're really focusing on that higher level concept. Next slide, please. For example, I use this is actually from the handbook. I use this in my classes to just help them understand the concept of inference. It's a process. We start with some process or population of interest. In the real world, we can never get 100% perfect sample. We can't get a truly random sample. In election polling, people won't talk to you and things like that. So there's some subset of that we actually sample from. We calculate a statistic. But then what we're doing is saying, we don't want to talk about the data in front of us. We want to talk about the entire population from which this came. Now, as I said, for many of you on the call, this is obvious. I'm going to say for most students, it's not obvious when they first hear about t-tests and f-tests and that type of thing. Now, how do we actually draw an inference about a population from a sample? That's on the next slide. There's a process for doing that. We define objectives and assumptions. We identify a variable of interest. We convert to a generic variable. Generic variable, for example, a z value, an F ratio, a T value. I frequently have students saying, what the heck are we doing with this Z? Why can't we just do it in pounds per square inch? Well, why do we have to create all this mumbo jumbo with T and F and P and all that stuff? And until they understand you're actually going through a process and there's a reason you're doing this, it's not really clear. Then we derive a probability distribution for that generic variable and draw appropriate conclusions on the basis of the laws of probability. So there is a logical thought process. It's just that students don't usually hear it. Next slide, please. So what's actually in there? It's an overview of the philosophy of point estimation, interval estimation, and hypothesis testing. We do address the p-value controversy. We explain the practical realities of the fact that random sampling isn't ideal, that's rarely achieved in practice. And then we do introduce probability distributions. It's not a text on probability. There's no urns with colored balls. It's really within the context of inference. Next.
Thank you, Roger. Excellent. Well done. Our next speaker is Ronald Does. Now, Ronald outdoes most statisticians that I've ever met because unlike some others like George E.P. Box, who had two middle initials, E and P, which he told me one time meant Elvis Presley, Ronald has three middle initials. And he refuses to tell us what the J is, but MM, I think, means makes money, but I'm not sure, and perhaps he can clarify that. But to proceed with his more serious introduction, Ron received his PhD in mathematical statistics from the University of Leiden in the Netherlands. And once again, I must digress a little bit here because those of you who are from the United States know that, might know that perhaps when the Pilgrims invaded the North Atlantic coast of the United States, they came to Plymouth, Massachusetts. And prior to that, they left from Plymouth in England, and prior to that, they lived in Leiden. Now, Ronald assures us that he's not responsible for chasing them out of Leiden, but the jury's still out on that. Ronald is a fellow of the American Society for Equality and of the American Statistical Association, elected member of the International Statistical Institute, and academician in the International Academy for Quality. As I mentioned earlier, he received ASQ's Shewhart Award. He also received the Lancaster Medal and the Hunter Award. And he's also awarded by the European Network for Business and Industrial Statistics the Box Medal. Maybe that's where he got his extra middle initial. Ronald has 10 books he's authored and more than 200 papers in the fields of statistics and psychometrics, process improvement, and so on. Ronald just retired from University of Amsterdam and claims that he's going to have copious free time. I believe the jury is still out on that, but we shall see. So, Ronald, it's up to you to do chapter 6, if you would, please.
Yes, thank you very much, Lynn. When the statistical engineer arrives at chapter 6, the work has almost been done. So the statistical engineer has learned about the problem, and it is now time to search and select the most important influence factors and to generate the best solutions. In chapter 6, we discussed the process of solution identification and deployment as an iterative process. This process is characterized by phases of divergence and convergence. To successfully arrive at the best solutions, collaborations are crucial. Consultation of experts in the problem area, hints and clues about possible influence factors and solutions from subject matter experts, and early understanding of the managerial issues are crucial for success through solution identification and deployment. Selection of the best solution requires understanding what is fundamentally causing the problem. Therefore, this phase begins with the identification of possible factors causing the problem and defines a process for identifying the most prevalent factors that can be controlled, compensated, or eliminated. Finally, in this phase, the statistical engineer starts to anticipate what is needed for solution deployment. Once possible solutions are revealed, initial considerations about what is needed for deployment starts. Thereby, the process of preparing the organization and the key leader for deployment is commenced. Possible hurdles can be identified and timely actions to prevent or mitigate deployment obstacles can be taken. So you are more or less in the situation, you know that you are right, but how to convince the others that this solution should be the right one. Next slide, please. Solving a problem by advanced statistical inference requires more than a mere technical solution and deployment. To solve a problem and make a solution work, a broader perspective needs to be adopted. This makes the role of a statistical engineer challenging. One must be an expert in statistical engineering techniques and must also be an effective organizational leader. This later role requires that the statistical engineer also has organizational awareness and excellent influence and negotiation skills. Part of this role as an organizational leader is creating commitment and educating the workers in the near vicinity of the problems and its solutions. Beyond bringing a one-time solution, an effective statistical engineer brings the solutions and improves the system that gave rise to the problem in the first place. Thereby, future problem manifestations are prevented and better process control, early issue resolution, and improvement capabilities are developed. In this chapter, guidelines are given for the statistical engineer how to deal with these issues. Next slide, Lynn. You are already at the last slide, but okay, I can say something about good old Duran is clear about the distinction between improvement and control. Quality and process improvement is usually a short-term, intensive, project-oriented search for process improvement. Quality control is a long-term, less intensive monitoring activity aimed at detecting and responding of irregularities. In the final phase of a project, the statistical engineer adjusts the quality control system. On the one hand, the statistical engineer probably has implemented changes in the process, and these changes have to be reflected in the control system. On the other hand, the statistical engineer probably has gained new knowledge about the process, and this knowledge can be used to improve the control system. In this chapter, we describe some popular methods for quality control. The essence of these methods is that they systematize the day-to-day management of the processes. Sustainable solutions can be obtained by adjusting the quality assurance system, applying statistical process control, documenting the lessons learned, and to set up a system for continuous improvement. And now the last slide, Lynn. The results of the first statistical engineering projects are, amongst other success factors, determined by the impact of the applied tools and techniques. Let us assume that the statistical engineer has successfully executed his first project and achieved good improvements. As more statistical engineering projects are executed and the statistical engineering methodology is applied more broadly throughout the organization, questions about implementing statistical engineering in organization arise. Improvement and optimization of processes, products, and services have gained increased recognition as sound management practice. A common label for the organizational capability to improve and optimize processes, products, and services is continuous improvement, for which the dominant philosophy and methodology of statistical engineering has much to offer. To achieve the organizational capability to continuously improve the processes, services, and products, organizations face management challenges such as motivating the organizational adoption of statistical engineering, setting adequate goals and performance metrics for all involved in the statistical engineering implementation process, and subsequently managing the statistical engineering implementation process. In this chapter, also a framework for implementing statistical engineering is a given. It separates the implementation in 5 phases and further clarifies roles and responsibilities of different organizational functions. The framework structures the statistical engineering implementation process in several dimensions that are relevant for the statistical engineering implementation leader to understand. And the publication has been accepted in the journal Production Planning and Control, where a even more general setup is outlined. Thank you, Lynn.
Thank you very much, Ron. I'd like to add just a general commentary to all of what you've heard so far, based on my own personal experience. As I mentioned, I've been involved in corporate leadership of statistics functions and have had some degree of success in all of that. And then went into consulting about 12 years ago, and that's a roller coaster, of course. And not too long ago, about a year and a half ago, I got invited into a company that was really struggling, and particularly in their R&D organization. And at the same time, I was involved in the early stages of the development of ISEA, its formation, and then eventually the authoring of this handbook. And so working with it and reviewing the chapters with various authors, and I learned a great deal about statistical engineering. So even at this old age, it's possible for one to learn. And the client organization had asked me to come in and help out in their R&D organization. Things weren't right. Their credibility was in the tank, and they were not making any progress. And they asked me to start out on one particular project where they had been working on for about 7 years and were not able to resolve. They were getting consumer complaints, and everybody was pointing toward R&D to fix this, and R&D really didn't know how to fix it. I worked with some clients in that organization. I helped talk about the definition of the problem first off, and get an understanding of who was involved, who else was involved. All organizations have silos, and the R&D people there were in a silo, and people in the other silos were throwing stones and offering criticism, and not much by way of productive thinking. And so we started into examining the problem and the process and who was involved. And this is not your typical thing that's learned in a statistics program in university, but it was key to the success of this project. The person that I was working with had been on it for only about 2 years, and he was not able to make much headway. We designed an experiment. We got what I was calling earlier the right amount of the right kind of data. And maybe it was dumb luck, but I have a hunch that it was a combination of their technical expertise and some added statistical expertise that came to a wonderful aha moment. And with that, it kind of turned the organization around a bit. It started to build their credibility. That was a first step. And so I was invited back, probably because of that success, to work on other projects. And I got together with the entire R&D organization, and we had school. And we talked about statistical engineering. We didn't talk specifically about any particular methods of statistical inference, and we didn't argue about what software was better. We didn't try to prove things. We worked on strategies for implementation of improvement throughout their organization using the R&D technology. This has built the organization over the last year to the point where they are now sought after, and people understand that there is great value to the organization. It built the esteem of the organization, it built their success. It recognized them as a key component in the organization's success. So, and that is just one of many, many case studies, and something that perhaps I need to write up. By way of wrapping up, I just say that, if you're not an ISEA member, join, it's free. And if you go to, there's a website, the ISEA-Change website, you'll see a little icon in the upper right-hand corner, and that will get you in as a member, and then you can sign in. You click on the membership icon, and then once you're signed in as a member, It might take a day or so, but once you're signed in as a member, then you can click on the members only content and get to this handbook. So I would recommend that to your use. And use it as a handbook, use it as a reference book, and there's also some good edifying stories in that book, and there are some case studies. I think the book itself has something like 450 pages, and then if you add in the case studies, it's up to over 600 pages, so there's a lot to wade through there, but you'll find things are of great interest to you. I wanted also to mention that November 18th through 19th of this year, 9 o'clock in the morning to 2 p.m. Is the ISEA Summit. And so that's a 2-day summit. And the keynote speaker is Dr. Michael Jordan, who's professor of statistics and computer science at the University of California at Berkeley. He comes to statistical engineering from a slightly different perspective. It is refreshing to hear his views on all of this. We learn from each other, and he will be a great contributor to that session. There will be panel discussions about statistical engineering, and we'll present some more information about statistical engineering using case studies. And finally, there'll be some discussion of statistical engineering at NASA. So registration will open in early October. Announcements will appear in your inbox, and we would encourage you to attend that 2-day session in November 18th and 19th. Please put those on your calendar. So our promise is that we will listen to your feedback. If you have comments, questions, insults, we will listen to them all. We will take your feedback. In future, we will publish more information. We will have more people involved. We will modernize and keep modernizing to keep current. So right now we're in first edition. In the second edition, we will correct any errors. We've got a process in the works for doing that. We will add more case studies. And as the occasion arises, we will present the second edition. So we thank you so much for your participation in today's webinar. We'll check and see if there are some questions and comments here. Sherry, if you're still with us, have you seen any information coming in, any questions coming in from people? We see no questions as of 11:07. We'll wait just a couple minutes for others to offer questions, comments, and then we'll wrap it up.
No questions at this point, just some compliments that I'll pass on to you guys.
Okay, well, everybody, thank you so much. Speakers, thanks so much for your contributions. Nicely done. Attendees, thank you so much for being here, and we hope to see you again at the ISEA Summit. Take care, everybody. Signing off.